Hey everyone, this is Yuchin, and this is another episode of Live Weekly Contract Reviews. And today we're gonna review Pool Party. And Pool Party is an app on Near that is similar to Pool Together on Ethereum. And idea here is kind of a raffle that is giving away free winning. So everyone pulls together into one big contract, and this money allocation usually goes to some compounding interest account. In case of Near, it goes to the staking pool where it's staked, and then once a day, the contract gets staking rewards out of the staking pool and distributes them. And
Distributes them to everyone, or how?
okay, so it distributes to one winner of this raffle every day, and you can buy multiple entries, and one entry costs something, and then your probability increases with the number of entries you buy. And it has very cool implementation how it does this. So let's jump into the contract.
So a no-loss lottery.
Correct. So the contract is implemented in AssemblyScript, and it has usually two files. One of them is model, which defines a bunch of classes and also a bunch of collections. And the main contract. So there's a bunch of get methods and a bunch of change methods. In AssemblyScript, there's no mute call or like mute self because there's no object that is like a singleton object. Instead, you have ability to serialize and deserialize objects on demand. So there's a few constants. So this is for testnet. And there's also Guardian. Guardian is kind of like the used owner of the contract. So you have a account owner, and this uses Guardian. So you can get and change Guardian. This is the method that verifies that you are the Guardian. So you cannot really, I wonder, oh. Then we delete the Guardian. And we reserve the new Guardian.
Feels like we should check if there's if it's valid, but hey, valid account.
Yeah.
I'm not sure if there's a easier way to do that like there is in Near SDKRS.
Users to ID. So user 0 is going to be the Guardian for some reason.
So only the Guardian can change the Guardian, but if you fat finger it and set an invalid account, you brick the contract.
Yeah, but that's
blockchain, baby.
Not as expected. Yeah, why would you need to change the user index? Why the Guardian has to be user 0? This is what I'm not quite sure. Like, why Guardian has to be always user 0? I guess it's to dedicate stake to the guardian or something like this, but then why not just register a new user? Anyway, so getting pool price. So if there's a price, then we return it, otherwise not. Get pool tickets. Pool tickets. Right.
Something I would recommend, which seems like pretty straightforward to implement in AssemblyScript, is something like the storage key thing that's currently being added to SDK-RS, just to shorten these keys and use constants throughout the contract for them instead.
Yeah. So that's a bunch of getters. So get to on stake. Get to winners. Array returns the last 10. Okay. Winner. So it returns the last 10. Then get pool info, which means the state of this is going to grow. Maybe not. Maybe instead of doing it, if you only care about last 10, we can use a rolling buffer of 10 last winners. Okay, get pool info, returns a pool. So you get number of tickets to on stake. Okay. I guess tickets are in balance as well. Next raffle, timestamp, get pool price.
What is
CLAN
telling you with the red underlines?
It complains that this is not a valid TypeScript. So it's like types are different. It's saying get pool is U64 and this is U64, and well, you're trying to get U64, but it's not a number. Like you get in a number. So it's because of like U64 is some like JSON serializable type into the string.
I forget, does AssemblyScript have like capital U128?
No, it just works with the, it doesn't have U128 type, so this one is a new type from BigInt.
So it is just using the lowercase u serializes as strings.
Yep. Yes. Okay, it just returns a bunch of info and whether withdraw ready from epoch height. And this is returns the NF epoch type. This is cool. Maybe it doesn't need to be more, and it should be equal. Maybe more. Unclear. Maybe here it should be, if the current epoch is at least the next on stake epoch, then we're ready to withdraw. Get account ID returns the user. Get account. If we don't have it, then we return a new user, basically nothing. Otherwise, we get the index and then we get number of tickets by this user and then total unstaked value when user withdraw turn. And unstake turn 0 now is more than when or equal, and there's some balance. Okay, wouldn't this overflow, underflow? When you subtract two U64s? Because then if it doesn't, then why do we need this check? But I don't think default is to panic in AssemblyScript, so it will silently overflow potentially. Even so, the frontend probably ignores this issue. Okay, get user tickets, return this, or panic if it's invalid value. And same here, if the index is not available. Not sure why it's I32 instead of U32, because index starts from 0, so maybe this one expects the persistent vector. The default, oh yeah, it is expects I32. I think it was because of the DQ. So DQ operates on negative indices. And accumulated weight is the how that works. All right, we'll find out. Okay, check internal. It has to be the contract itself, so it's a private method. Then we get the results, and the results has to be more than 0. Okay, this is testing. Status equal to 1. It would be good to have a constant here, which means it's, I assume it's a failure, so 0 is okay. All right, so pool arguments. This is a promise. No, that's not a pro. It's a argument. That's how you can define a public field. Update price. So we verify that we have enough gas, which is a bot load, I assume, which is 300 teragas. Then we call get account on the pool for our account and have a callback to ourselves to update price as a callback without arguments. And we return it as a result. Cool. So this is not strictly necessary because entire method will be rolled back if these two promises cannot get scheduled. So pretty much it will get there and then roll back probably somewhere here, like whenever you run out of gas, and nothing will change. This can also be moved to constants. So this is pretty low because it's a single read. So it can be 5 teragas. This can be, we'll see, probably not much because it doesn't do anything either. Another 5 teragas. Joining them and spawning is 20 teragas. So you need about 30 teragas for this. And for this execution, another 5, so 35 teragas. I think we'll need to add more info on the best practices for the gas, and that can be referenced for in AssemblyScript as well as a documentation, like cheat sheet. Okay, we call change internal that returned us a promise result, and then we decode the buffer. So we should get a user, which is interesting because this is a pool user or like a staking pool account. So I would rename it from user to staking pool account because there's two conflicting pieces. So one of them is like get account. And another one is information that's returned by the pool. So I would prefer just two different structures. Get pool tickets. So we get the amount of tickets, the price. If the balance is larger than what we staked in the past, staked balance in external pool and the tickets in our pool is the price. That's right. Then we log that the price is this and we update the price. So this method can be called by anyone. Well, actually not because of the, it is, yes. It can be called by anyone to update the price. It's similar to ping on a staking pool. But also you may need to ping the pool if the pool didn't ping itself. Otherwise, you will not get the updated info on the pool, but it's not a problem most of the time. Okay, next, stake tickets 4. This is not exported method, so this is internal. We update amounts and this is a binary tree, a full binary tree essentially, except the last row is not pre-allocated. And we always add at the bottom. And then element at position 1 is kind of our root, which means if you go to the left, it's 2 multiplied by 2. If you go to the right, it's multiplied by 2 plus 1. What I don't understand here is how the initial index is given and where it starts. So like it would define the limit of the tree. But that's how you increase the binary tree at a given position. You basically start from the bottom and it goes up until you reach the root node. And then you set that the amount has increased. Okay, deposit and stake. So this exported, so anyone can call it as well. We verify that we have again a boatload of gas. Then total number of users. We get the guardian. If n equals to 0, which means the guardian has to make a first deposit. Cool. Then we add amount, stake price. Wait a second. So why? Okay, we add 100 Yoctanir to the staking amount because there's some rounding errors. So it's not 100, it's usually like 1 at a Yocta, but there can be some slippage, but yeah, that's interesting. So this will come back from gas burnt on this contract. Then we create a promise towards a pool to deposit and stake. We attach 100 teragas, I assume. 100 teragas and this amount. And then we call our callback with the amount we just called. Okay, and let's see. So we verified that it was success. And if the sender, yeah, you don't want to do this. So sender, I think sender is signer. So signer is different. Basically, it assumes that the signer of this transaction is the one who called deposit and stake. But it may not be the case because the money can come from like your escrow account. So the predecessor is the one who attached the tokens instead of the signer. And in this case, the way to resolve it is just to add in the arguments the predecessor who created this account. And this one, again, uses the sender, but it should use the predecessor. Yeah, so every time we verify access, we should, instead of relying on signer access ID, we should rely on the predecessor. So pretty much almost everywhere, instead of using sender, we should use predecessor. This is a more secure way of doing results, because what I can do is, let's say I have a contract that the guardian calls, can be some other app, and then it would call this contract to change the guardian. And this contract will trust that it was called by the guardian while the guardian was calling some other contract, let's say some kind of other game or app. And that's why you have to rely on the predecessor, because if you call directly this contract, then you are the predecessor in addition to the signer. But if you call this contract indirectly, then you don't want to do this. So pretty much you have to replace, I assume, most senders with the predecessor. Okay, let's come back to the where we were doing this. So including here, it should be predecessor. Okay, so here you want to have context predecessor as the input. So instead of relying on a sender here, you want to rely on a context predecessor that was passed here. So you want to have account ID as an argument to this method. Okay, so if the method exists, then we're gonna stake on existing user. If the method doesn't exist, then we will set an index to the next total number of users. But if we do this, the accumulated weight is not really a not really a tree anymore. So I'm not sure how that sync works. Because the way you implement a binary tree is something like this. So you start with a node 1. This is node 2 and 3. This is node 4, 5, 6, 7. And then the final row is your leaves, which is like 8, 9, 8, 9, 10, 11, and so on. So let's ignore the final row, and this is going to be our leaves. So this is your account IDs, and that's why if your account ID is, in this case, it is 1, so you start from 1, but your 1 should be the root. And then you compute the sum of this. Well, maybe it's kind of some other binary tree implementation that maybe works this way. Because you only care not of the sum of this, but sum of all the previous one. I guess, yeah, I guess it works this way. Okay, then it's fine. Because you care about the accumulated weight up to this point, and then you're recursively reconstructing it. Because this one, for 6, it's the sum of these two plus 6. So in this case, so for the first user, you will have a sum, let's say 100. Now, when you're a second user, you will have a sum of, let's say 200, but you also will do plus 200 here. So your sum of 1 gonna be 300, but sum of 2 gonna be 200. I'm not sure if it's the right way of doing it. Okay, we'll find out when you actually use this. So yeah, we basically added a new user, and then we say stake tickets for this user, for this new index, and return true. But we don't use info, so we don't care about what deposit return. Now on stake, let's actually come back to on stake a bit later, because I want to check how the prices are computed, or like how the random works, the raffle. Okay, so random U128, it takes the minimum, maximum, does the mod, and then returns minimum. U mass random buffer. Okay, what is a random buffer? Wait, where is this code? Okay. Okay. That's actually a fairly interesting way of doing the random seeds. I haven't seen it on AssemblyScript, but the idea is if we get a seed in this block, then we will reuse it. But the seed has changed, and right now the seed is unique for every action that is called, so it's unique per function call. In theory, that should be like a singleton, a random buffer singleton should be in memory. And then we do hashes and continue reading. Anyway, it's kind of cool. And I think it works reasonably well. So we get the U128 and then we use mod. So U128 is pretty large, so this shouldn't be a big issue with the like trailing around him. Okay, raffle. So we check the current time and we check when the next raffle should be. We verified that not there should be enough time between this. Now we get the, if there's more than one user, random ticket 0 accumulated weight 0. What is accumulated weight 0? So we compute the winning ticket, which is essentially some byte. Some kind of guardian. And then
Where do those come from? Just those variables, user tickets and accumulated weights.
So user tickets is the amount of stake you have
Like
per user.
in this function, is it a top
But
level?
Yeah, that's a persistent vectors. But what is the 0 is not totally clear to me. Okay, so 0 is a root. This is for sure. So my math was not correct. So you have 0, that is 0. Then index 1, let's say the first user, it's staked 100. Then the second user staked 200. So we divide to wait. Stake tickets for. Okay, so we divide index -1 divided by 2. So for user 2, it's gonna be 1. Oh, it's gonna be 0. So total gonna be 200. It's okay. For the first, we first add 300, right? So let's say next user comes in, user 3, and stakes 350. Then we divide it, so it's getting index -1 divided by 2. So we increase this one and also increase the first one. Okay. Let's see how we select the winner from this. The winning ticket less than user tickets. So this is starting from a tree, starting from 0, left and right. That's correct. if the winning ticket less than this, oh, I see. What is, so if it's more than that and left, then we go to the left and we remove this. If it, otherwise we go to the right. And remove both that user and the weight on the left. We always check the weight on the left. Some magic that is combined extra n. So basically the final row is in user tickets in a regular binary sum tree. Let me copy my piece out of here. So I need, this is a cum way, and then I need to have user tickets, which gonna be, I didn't add 0, so let's add, let's say 50 to 0. So you have 50, this one was 100, this was 200 and 350. So let's say we wanna, we have total of 700, and let's say we're trying to pick ticket number 300. So we're starting from here, and is it less than 0? No. Then is it less than 0 plus left? Left is 450. Yes, so we go to the left. So basically, we went to the left part of the tree. 50 plus 450, yeah, 500. Then we remove only ticket 0. So index became 1. Now left is 3. And right the right is 4. Well, we don't really have 4 and we don't use 4. Okay, we go here again and index is 1. So is this less? Oh, weight becomes 250. Guess I can say index 0, weight 300. Now index 1, weight 250. So we go here, it's not true. So we check, is it index 100 plus 350? And it is true again. So we subtract so index became 2. No, index became 3. Weight became 150. So we go here and it's true. So the third one won, but it shouldn't be the case. The second one should have won. So anyway, so this one, it better be explored a bit more. So I'm a bit confused on the accumulated weights. Because it's like magically growing the tree, but maybe it works and I just not quite sure how that works. Well, let's finish this. So once you got the winning ID, you get a prize from the pool, and then you keep the reserve. Is 20, so 5% goes to reserve, and they go to Guardian, and the rest goes to the user who won. Then we say how much went to where, and then we do the next raffle after raffle weight, and then we set the price to 0, and we report that this person won by adding them to the list of winners. This is cool. Maybe also check that the price is positive, so you don't do anything like this. So you cannot have a raffle until the price is positive.
Yeah, this is such a cool pattern. I'm kind of jealous that someone made this. I've been wanting to do this as well. This is really neat.
Okay, let's go to the methods that we skipped to just quickly make sure that nothing crazy happens here. So unstaking, checking enough gas, verify. Again, you need to verify that this is predecessors, not a sender. Getting a user, then getting the amount of tickets. It verified that you unstaking less than this amount, saying you want to unstake. Get to unstake. What? Oh, getting how much you want to unstake. Increase this amount. So we need to unstake more. Getting unstake turn +2. User will be withdrawing 2 turns. The turn, I actually don't know what is a turn. And where we increase it, we'll find out. It's about like 22 hours or something like this. Okay, user tickets decreased, user unstaked increased, accumulated weight decreased, and we go up the tree and decrease accumulated weights as well. Yeah, so this binary tree a bit shaky because it uses this value and the parent's value in the same place. So for example, user 1 matches the accumulated weight as a node at the index 1, while it shouldn't be like this. But yeah, I can check this later and like figure out if it's a right way of doing this or not. Okay, next, withdrawal. So to withdraw, you need a ton of money, verify user, same stuff, same stuff. Withdraw turn, default is 1. If withdraw is more than the user withdraw turn, withdraw not ready. So you cannot withdraw after you staked immediately because you need to call on stake. We create arguments with index and amount. Then we create a promise. And then we transfer this amount, the full unstaked amount, to the user, and we call withdraw all. What we didn't do is to react. So we didn't like clean it up anything. So I can call twice withdraw all potentially, and it will schedule 2 transfers to me, which is not good. So this is probably an issue for the contract, because you can like schedule multiple withdrawals, and until you have withdraw all succeeded, you will drain this. So you want to have this zeroed out here. So you want to set this one to 0, but on case of failure, this is where you want to refund it. But what you're doing is I basically can do a batch call to withdraw all and like drain this account multiple times, and then callbacks will start to arrive. It's like, yeah, user succeeded, good job.
That's interesting. That's almost the exact pattern you're supposed to do for reentrancy attacks, but it applies here to async promises. That's kind of neat.
Yeah. So yeah, basically, yeah, to do set amount to 0. So yeah, you want to do this, and then instead of check internal, do make it reverse. If failed, refund. So basically, anyway, next is withdraw external. So this one gonna call you need to call on stake on external first. Then next on stake epoch height must not enough time passed. We call withdraw all. So it will withdraw all, then stake balance, and then we gotta get the callback, and we will increment the withdraw turn. Now on stake external, I assume does the same stuff, except you need to call withdraw external first. So this all can be bundled into ping. It will like should do something like, oh, should I unstake or withdraw? Unstake. Let's do unstaking. Should I withdraw? Let's withdraw. So to unstake, if nothing to unstake, then we call it and unstake and pass this argument to unstake. And then again, same issue here is this method can be called multiple times. While withdraw all doesn't matter, it kind of matters that this sync arrives. So we can increment withdraw turn by multiple times, and that will break the contract. Like you will have to call on stake multiple times, but it's a bit weird. So the issue again is you're not protected that this method is not called multiple times before this one happens, because it did not modify the stake yet. So what it should do, it either should like say, okay, withdraw turn is now 1, but wait, it's not completed yet. So the turn is not completed, so it locks that operation from doing it again until this callback arise. So when callback arise, it's like, okay, let's unblock. But then it should be careful not to panic here. And stake external does the same thing, just in stakes. And then when it arrives, it updates the amount of tickets to raffle. Then next on state epoch plus on stake epoch, which is 4. Good. Increment and stake turn into and stake set to 0. So it succeeded. Yeah. Okay, and yeah, the rest we have looked. So yeah, there's just a few things. The best way to do this. First, make sure you check predecessor instead of sender almost everywhere. Second, guard all methods with some kind of internal lock. And the way you would do this is especially one that interact with the staking pool. Once you verify that this action is possible and has to do, log the contract into something like doing work with pool. Then verify next time the withdraw external code, verify that it's not doing any work right now. And then once the callback arrives, need to be careful not to panic until you unlock the staking pool. What I saw in stake token do, they attach another promise that all it does is just removes this blocker. So you can do the same. You basically allow this promise to fail, but the next promise after this will unlock this contract and restore the state. So this way, kind of interesting way of doing it as well. And finally, I'm not sure this binary tree works correctly because on this example that I did, it looks like it didn't work out that well. Because I expected second user would win with 300, but the third one won. Unless I miscalculated weights, but I don't think I did. Okay, so that's it for this contract. I think this is really cool pattern, and like using this binary tree definitely makes a lot of sense, and it allows you to, in logarithmic time, to find one user in like supporting very large number of users. So this pattern of this kind of like accumulative binary tree, probably worth to move it to some type of collection because it's fairly common where you need to do this kind of action. But the indexes probably has to be going other direction than the forward direction, or I'm not sure, because when the tree is full, so I have this tree drawn somewhere right here. When the tree is full, so what you need to do for the next user, you basically have to do indexes of this tree should be like starting here, then you add a node here, then you add a node there, and finally you add a top node between these two. So this is the nodes you need when you add a new element to the bottom row. because maybe it works for accumulation tree, but I don't know. Anyway, so that was to be checked. Well, the next element will not add any new node except for this node. It will only add y. Then the next element, like z, will add this node and that node. And this node exists. Does this make sense? What I'm drawing here without edges?
Yeah, it makes sense to me.
Okay, then I think we can stop. And I actually haven't looked in the tests, but there's actual tests that doing something. So it does binary tree.
This could be the most interesting AssemblyScript contract that we've reviewed or I've seen. It's really cool. I'm glad we got to do it this time.
So it does have some logic. So maybe it does work, and then maybe I didn't understand how it's updated or like something else. And I believe it probably possible with the same number of elements because we are not doing like full tree. We only care about accumulation tree. But maybe I misunderstood how it works. And that's it does look like have a bunch of tests, so maybe it's covered. Okay, thanks everyone for listening and joining. This was very cool contract. I really like the accumulation binary tree implementation. And yeah, see you next time. Bye.